thank you everyone who registered and everyone who's joining the webinar. Today with me, we have Dr. Andrea Costa from TEDIEL. And this webinar will be about the possibility of unlocking quantum innovation thanks to the Photonics Bundle. So thank you, Andrea, for co-hosting this webinar with me. And we can just start stating what is the nature of the collaboration between FLIM Labs and TEDIEL. But before we're going to give you quick overview about the two companies, so FLIM Labs and TEDIEL, and why we decided to embark on this partnership, in this commercial partnership. So FLIM Labs is an Italian company, and FLIM Labs has a vision of democratizing fluorescence lifetime analysis in general, so single point analysis, but also imaging. And the mission is to deliver, let's say, reliable, portable, and affordable instrumentation and software for accomplishing such a task. So maybe you know already that FLIM Labs was founded in 2019, and then in 2020 until 2022 secured funds for developing this new technological framework for fluorescence lifetime analysis. And then from 2023, our products are on the market, and actually in 2024 and 2025, we started to use our products for certain application, but also we started to make partnership both with microscopy companies, but also with other companies like TEDIEL. What we do, we develop hardware for fluorescence lifetime analysis, meaning lasers, detectors, but also we develop software, and we can focus, let's say, our software development on imaging with a software named FLIM Imager, and together that can be used in conjunction with some Python apps, which are meant for single point analysis, and they are three. It's like an app for tracing the intensity, an app for doing TCSPC analysis, and an app for doing fluorescence correlation spectroscopy. And this is a nutshell what FLIM Labs is about. So I'm leaving the word to Andrea, who will give you an introduction about TEDIEL.
Thank you, Alessandro, for the introduction. I'm Andrea Costa, and I work as an application engineer for TEDIEL SRL, which is a spin-off company of Politecnico di Milano, established in 2019. And ever since, the main objective was to bring to the market the technology that was developed and still is developed in the digital electronic lab of Politecnico di Milano, which mainly is related on time circuits. So what we do and what we will show you today is our time taggers. But not only that, the knowledge that we have built upon these devices has also allowed us to deliver custom embedded systems that can serve multiple purposes and in different fields. So some of our main partners, apart from FLIM Labs, which was already introduced, are Elettrasynchrotron di Trieste, which is a multidisciplinary research center placed in Trieste. For example, they use our time to digital converter IP core in their custom PCBs. And another one is Nereos, which is a spin-off company of Politecnico di Milano as well, mainly dealing with spectroscopy devices. And I'm pretty sure that at least one of these you have heard about. So this is the index for today's presentation. We are going to first cover an hardware overview regarding the bundle itself and the devices it is composed of. And then we are switching to a more practical part of the webinar, onto which we are covering the software and the functionalities that you can unlock with our time tagger merged with FLIM Labs SPAD detector and laser. So this is the Quantum Photonics Bundle. As you may see, we have 3 different hardware devices plus a host PC. The first one is the fiber-coupled picosecond-pulsed laser from FLIM Labs. Then we have the time tagger from TEDIEL, and the single-photon detector, the SPAD from FLIM Labs as well. the software that we use for processing all the information is the so-called TDC software by TEDIEL. I don't know, Alessandro, if you want to.
No, thank you. Thank you.
The laser.
Talking about the lasers, what I could tell you more about the specification about the lasers. The lasers are a standalone module, meaning that inside the same box you get the driver as well as the laser source. A laser source that is available in several different wavelengths. So we offer from 4 or 5 nanometer up to 850 nanometer. These lasers are pulse lasers, meaning that they emit pulses of light down to with a maximum of 50 picoseconds. The peak power of each pulse is about 160 milliwatts, and the maximum repetition rate is 80 megahertz. So in the end, when operating in pulse modality, these lasers are capable of giving out, on average, little more than 1 milliwatt average power at 80 megahertz. It's interesting to note that these lasers, we engineer them to be already fiber coupled, meaning that inside we have a laser diode which is fiber pigtailed with a monomode fiber, allowing these lasers to be used for single point application but also for imaging. In fact, you can see here in this slide that when you use fiber optics to let's say to connect to the laser and to bring the laser light wherever you need, and if you connect it to a collimator, these are the figure of means that we can achieve. So this is the beam quality of our lasers when using a fiber optics and a collimator. Then, since we are diving into time resolved measurements and TCSPC measurement more in general, the idea of these lasers is that whenever a pulse is emitted, an optical pulse is emitted, there is also a digital electronic signal that is, let's say, outputted by the device. And here you can see that the laser has a sync, so a digital sync out, capable of giving you as output the real repetition rate the laser is working at. So we can go from 80 megahertz to 40 megahertz down to 1.25 megahertz when using the internal clock. While we also implemented another modality of working. Andrea, maybe if you can change. Yes, another modality of working, meaning that here in green, you can see the internal triggering from 80 down to 1.25 megas. While the user can also select the lasers to be externally triggered. And in this way, in this working modality, when the laser is basically fed a trigger signal, a digital trigger signal is capable of outputting optical pulses. The functionality is called pulses on demand. Here you can see that for each rising edge of a digital laser trigger, we can get basically an optical pulse coming out of the receptacle. And this is, in a nutshell, all the functionality of the laser. In a nutshell, also, let me talk you about the SPA detectors. The technology is well known, so single-photon avalanche diode. Both these detectors are fiber coupled. The detector sensitive area is 50 microns, and we offer in two versions. One that has a peak sensitivity in the blue, around 450 nanometer, which we call the blue shifted, while the other version has a peak sensitivity around 630 nanometer, which we call the red shifted. The two detectors from a mechanical and electronical perspective are alike, and the principle of functionment, the main function is the one that we see in the next slide. We get one photon in, and we get a digital output out. So for each photon, this detector is capable of outputting a digital signal that basically tells us that a photon has been detected. Maybe something to mention is that we equip the, yes, go ahead on slide number 20. Something to mention is that we equip the laser with a metal base, with a metal plate that facilitate the laser to be secured on any type of surface, like optical table or a mechanical support. So I'm leaving back the stage to Andrea, who will tell you more about the Felix.
Thank you, Alessandro. I also want to spend just a few words regarding the Felix TDC. I will list a few of the characteristics that make this a beautiful timetagger for quantum application in this case. As you may see from the slide, and also I have it in my hand here, you can see the dimensions in real life. We have 3 channels that can be used for inputs. One of them is aimed for the laser, for example. If one wants to go up to frequencies like 150 megahertz, we can support it. And the other 2 measurement channels are for example, for the detectors. It has USB-C connectivity, and is supplied by a 5-volt barrel jack to have a quite simple way to turn it on and use it. To summarize the performance, we have here a few of the characteristics. So we have 12 picosecond RMS timing precision. So the jitter contribution from one channel is this 12 picosecond RMS. We have down to 10 nanoseconds dead time on each channel. So if I detect a photon at time 0, I can detect a new photon after 10 nanoseconds on that same channel. We have a global measurement rate, so all the channels used can support up to 140 megasamples per second. And per single channel, not the sync, but the measurement channels, we can go up to 80 megasample per each channel. Linearity is also good. You can check both DNL and INL, which are pretty low. The way we work with external signal is to detect on a leading or falling edge. We have the input that can accept signals going from 0 to 3.3 volts with a tunable threshold that can be tuned from the software to a value that goes from 0 to 2.5 volts. We have onboard histogramming, which is a unique feature that not all manufacturers of timetagger offer, and it's really important to have, because you can compress data and not need to output a stream of timestamps that then need to be processed, but you can directly output from the device a compressed file which represents the time differences of the selected events on the channels. But of course, you may also like the idea of transferring the raw timestamps to your PC for further processing, which is an option to work with this device. Now to access these functionalities, we have a couple of different ways. So the first one is to use our friendly graphical user interface, which I will show you in a minute, and that will be the easiest way for any user to get started with our functionalities. But then all the functionalities that I will show you via the GUI are also available from our Python or C++ APIs, meaning that integration is available. So one can script any of their instruments to be used together with our instrument as well. And all of our software is available both for Linux and Windows operating systems. So thank you for listening to this part of the presentation. And now we can switch to the practical part where we show the software.
So maybe if I may tell you more about this part. So we basically, in this part, maybe Andrea can show you, we connected the Quantum Photonics Bundle to a cuvette setup.
Yeah. Do you want me, Alessandro, to show the setup with my webcam?
No, I think it's okay. I mean, we're gonna just, you know, like tell the audience that we connected the Quantum Photonics Bundle to a cuvette setup, in which is we have a cuvette, and the cuvette, and of course we have a fluorescence filter. We're gonna perform a IRF measurement in which the cuvette we filled with some water and some milk to give you, you know, let's say, to make the sample scatter so that we can collect the scattering and reconstruct the IRF. And then in the same cuvette, we are gonna inject a fluorescent dye to show you how the TDC software can reconstruct not only the IRF but the decay profile. In the end, I mean, the TDC software takes all the time tags of the incoming photon and process them in the way that we prefer. So, Andrea, please go ahead.
Thank you, Alessandro, for pointing out the setup. So you can see that this is the GUI, and I just connected on click because on connect because I had my device already connected to my PC. And as soon as I click on connect, you can see that here you have the serial number of the device that is connected and a list of modules that are available to work with. So basically, the first one would be the counters, and this view refers to the module that actually takes the input pulses that are triggering our comparators and giving a sample on our device. So you can see that now I have connected my laser to channel number 1, and you can see that the frequency is 1.25 megahertz sharp, whereas on channel number 2 is the detector, so the spud, and the light that is emitted from the laser triggers, as Alessandro said, a cuvette that contains milk solution with scatters, and we can then see what information will bring with these events. But how to configure the device? So basically, we have the channel configuration view, which allows us to tune the voltage of the comparators on our devices. And knowing that, for example, the laser brings a signal that is 2.5 volts, if I move my threshold up to more than that, at some point I lose the triggering of my signal. So if I go back to a value that falls within the range of the pulse given by the laser, the counts that are also visualized right here go back to my to the correct trigger rate by the laser. For each channel, you can decide to also move the threshold accordingly, which eases the process of setting up multiple channels if you had, for example, multiple detectors outputting the same voltage range. And in the case of time taggers with multiple channels, there is also this view, which summarizes as well in a list view the configuration for those channels. One other parameter that can be tuned from this view is the virtual delay. So let's say that you have your setup, but the path, the length of the cable that brings the laser signal to the device is longer, and you want to tune it, as we will see in just a minute. You can do it from this setting right here. But let's go to the acquisition modes. I want to show you the histogram, which is what we will mainly use today. It has some configurations. Some of those are simple, and there are also more advanced ones which we will not see today. But for example, if I go, we can see that we have 2 instances of histograms in our device, which are just the same. So it's a module that is replicated twice on our device, so we can take 2 histograms at the same moment. And we want to use, as we said, as reference, so the minuend of the subtraction for the time difference, the laser, which was on channel 1, and for measurement, channel number 2, which holds the spot detector. We can then select the range. For example, I want to go up to 1 microsecond, let's say, of full-scale range. We will have the binning necessary to reach that full-scale range. But let's go on enable and see what I see on the device. So from this view, you can see that now I enable the device. I can see a peak which is close to the origin, and everything goes to 0 after 800 nanoseconds, because my counter, my 1.25 megahertz, will then have a period which lasts 800 nanoseconds. So after 800 nanoseconds, my counts will go to 0. I will show it you better in a chart view. What is a chart view? This can be thought of as the configuration view of the histogram. But in order for you to better see the histogramming data, one can click on the view and set a new chart view. This will open a window that will be also available for being navigated through. We can see that we have this peak, which corresponds to the IRF, which we want to measure. And then we have some other beams that are populated with lower counts. All right. Now, if you want to see a little better the IRF, we may shrink the range and let's say zoom in a bit more on the peak. So let's say that we want to go to 125 nanoseconds. You will see that the peak is now a bit more zoomed in, which is just after 40 nanoseconds. And I may also want to minimize the beam width so that the beam of the histogram is as little as necessary to cover all that range. And if I now go back to the same graph as before, I can see that the IRF is a bit more sharp and can be seen a little better. Now, I was talking also about the possibility of moving the delays of one channel with respect to another one. In this case, we may want to move this peak towards the origin. And how may I do this? So if I'm taking the reference and every photon that arrives, I refer to the reference, and it comes at 40 nanoseconds, it means that if I delay my laser, which is on channel number 1, by 40 nanoseconds, and I now go back on the histogram, I can see that it moved. It was at 40 nanoseconds. It has now shifted towards the origin of my graph. So here is the 0. Now I have my peak at around 2 nanoseconds. For every chart view, so this is live, this is happening live, and we are refreshing our histogram every second. We may also want to check real-time modification of this histogram by lowering the refresh time, and you will see that this now moves a lot quicker, so it's refreshed live. And we may want to either see it just refreshing, and you can see that the peak counts are around 5K on the scale. But if you want to accumulate for more time, you can also toggle on this accumulate switch, which will make the histogram start accumulating until I stop it. So you can see that now the scale is increasing as the time passes. If I want to check, for example, some statistics on my histogram, for example, I can see that the mean, the mathematical mean of the histogram is around 9 nanoseconds, but that's just because let's show it in the logarithmic axis. There are a lot of counts which come from after the peak, and this means that the average will move towards the left, towards the right. I can also check, for example, the standard, and I can see that if I zoom a little bit in on the histogram itself, on the peak itself, I can see that the chart standard reduces, and now we are seeing 236 picoseconds of sigma regarding just to this peak, which, if I show it again in linear, is comprehending a lot of also not really good data on the right. So if I zoom in a little more, you can see that the overall quantum photonics setup can deliver just without any optimization around 200 picoseconds of RMS jitter. So what now? What if I want to export this data? The simplest way is just to click on Save Chart up on the right. And of course, PNG and JPEG will be taking a screenshot of this histogram. And CSV will export as well the data regarding to the histogram. For example, if I want to go to Documents and say, okay, let's just stick to Documents and open the destination folder. And I call it FLIM TEDIEL. And if I go to export, you can see that now I have exported my data, the two type of images that I selected, and the histogram, which if I open will show you just two columns regarding to the bin value and the count on that bin. So this is expressed in seconds, and you know that you can guess the binning by the fact that this is the time, and these are the counts. Probably the peak, you can see that we have 4,000 counts here. And if I go towards where the peak was, you can see the counts increasing a lot. So from 4K, we are now peaking at 1 million, 2 million, 3 million, and so on, which again reflects exactly this histogram right here. So these are what concerns the histogram. It's really comfortable to use, and you can have a really fast way of checking what your design is outputting. If I add, for example, now I have milk towards the end of the webinar, I will try to switch my cuvette with one containing a fluorescence sample, and this will then be the exponential decay regarding referring to the lifetime of that fluorophore. The other way of accumulating data, of taking the data out of our device, would be through this TTM, which stands for time tagging module, which will take the user to select what channels he wants to have. For example, now we have just channel 1 and channel 2. The type, the format, so what the data will look like in the file that is stored on your PC. Binary file is a more compressed format that is faster and allows for more throughput of data. And then again, the saving options on the file system, and the possibility to acquire for a certain amount of time, or to split based on the file dimensions, which just reflects what we did also with the histogram. But apart from this, I can also show you pretty quickly, if I, for example, move a little bit up the frequency of the laser. I now went up to 5 megahertz, for example, and with the other histogram that I have on board, I can check the period of the laser. Now, 5 megahertz should be around 200 nanoseconds. So if I go and want to check around 200 nanoseconds with a minimum time bit and see what it looks like, I can see that I have this really sharp Gaussian, which represents the jitter of the period of the laser from FLIM LABS in this case. And if I check on the standard of this graph, I can see that it's down to 8 picoseconds, which is a really nice number. And again, the acquisition is still the same if I want to save it, and so on. Yeah, having said this, Alessandro, do you want me to try really fast to change the sample? How are we?
Absolutely. Thanks for the nice explanation and the nice introduction on the software. Maybe meanwhile I talk, you can swap the cuvette,
Yeah.
drop some fluorescent dye and put also back the filter.
Yeah.
And the idea of this quantum photonics bundle is that because basically FLIM Labs is about measuring fluorescence lifetime. So also the specifications of our hardware and software regarding the FLIM data acquisition card are optimized for fluorescence lifetime measurement. If we want to move more into a quantum type of application, then of course the specs of our card are not sufficient anymore. So that's why we teamed up with TEDIEL to provide you the ultimate, let's say, an affordable solution for performing time tagging with a very high time resolution and time precision. So this is the point of the collaboration, and also this is also the point of TEDIEL, as you can see, is providing a time tagger, very compact, but most importantly, user-friendly. So now you see Andrea basically inside the cuvette put some fluorescent dye. He also plays a fluorescence filter. Here we are using a laser which is 488 nanometer, and the fluorescence filter is set to be a 500 nanometer long pass, and that's the decay profile that we retrieve. So of course we can use it for quantum application, so for measuring time arrival of photons, but also if you like for traditional fluorescence lifetime analysis measurements, so for traditional TCSPC measurements.
Exactly. As Alessandro said, I just changed the cuvette, and you can see that from the histogram, I cannot. I can see already the decay. This is shown in a logarithmic scale. I can also show it in linear scale, and it's not fitted because in our policies we prefer, for example, the user to fit the data with the best way he knows. So if he wants to fit two exponential, double exponential decay, or a single one, we are not outputting a value which we think is what should be shown. So one is completely free to take the data as a CSV, as we saw just a few minutes ago, and then process it, which is pretty simple, starting from an already computed histogram, and then grasp all the information that you want. So this is just to show you how quickly we managed to show an exponential decay with some simple setup that you can achieve with the Quantum Photonics Bundle. So again, three smart, compact, usable, portable components that are each really, really good in what they need to do. And yeah, you can. This is pretty much comparable to or better than whatever other manufacturer you may think of.
Andrea, maybe you want to spend a few words about the API that you
Yeah. So basically, what we did, everything that I showed you up to now can also be completely integrated in via Python bindings, C++ bindings. We also have LabVIEW bindings, which cover a bit less of all the characteristics that we have. And when importing our libraries, you are basically able to build how to say, you can open the device just like I did. Of course, it's a bit less intuitive because you cannot see a histogram. Of course, for example, a histogram is a visual tool. But if I now know that with 40 nanoseconds delay on channel number 1, with the full scale range of 125 nanoseconds, using channel 2 and channel 1 as a histogram. I know that I find my histogram being from 0 with the peak towards 3 nanoseconds. I can open the APIs and import the device. I can show you, for example, really quickly, let me try this out. Okay. Okay, I just had to habilitate the virtual environment. Let me also zoom in a bit more. Okay. This is PLIB TDC is the name of our library, and now I've just imported it. And what happens is that now I can build. I can build the object that is the backend of my device. I can get what devices are connected to my PC. For example, you can see that I have a Felix device connected, and for example, I can ask this backend to open the device and to load the modules that are on the device. And for example, I know that I will have one object called the TDC, which is going to be, for example, getted by a method that is called getTDC. And if I get this TDC, I will now have the possibility of having all the methods and stuff. You can see that I have possibility to see if the virtual delay that I talked to you before is available. I can check information on the period of the TDC, which is 2.4 nanoseconds, for example. You can grasp a lot of information without difficulties. Of course, these APIs are documented, and we will also have the documentation of the APIs, which allows the user, of course, to understand a bit more on how to use them. For example, I know that I have counters. If I want to check the counts, I can just go and say mb.get TDC counter. And if I have now this counter, I can take the counts, and I know that in 1 second I had 5 million events on channel number 1, which was the laser, and also 5 million events on the detector. So it resembles what I also had from the software. And this is just to show you how simple it is to get started with also the APIs. It just reflects the GUI that we show. Of course, setting up a measurement just like the histogram requires to set up a few more parameters, but in the end, by following the documentation, it's pretty easy to get started with this as well. I don't know, Alessandro, if you wanted to have a few.
No, I think for sure. I mean, on the website, both FLIM Labs website and TEDIEL website, there are plenty of information about the API and where to get them. So I would say this is all for today, and I hope you enjoyed the presentation of the Quantum Photonics Bundle. We recorded this session, which will be uploaded on the YouTube channel for future reference, and we'll also include in the description all the links that you might find useful to gather more info about the bundle. For sure, you can get in touch with us via email. So we are also available for a one-to-one video call if needed. So thank you, everyone. I'm gonna close this Zoom meeting, and thank you, Andrea, again. Thanks
to Alessandro
for
having me, and for the nice collaboration that we set up.
For sure. Ciao, bye.
Bye, everyone.